Hey everyone, this is Meyer, and as I was getting ready to release my latest masterclass in FL Studio, I kind of had this anxiety that no one would want to sign up, that people wouldn't be interested in learning music production due to AI tools like Suno that allow people to basically create songs. And then I realized it's probably even scarier to be someone who's interested in becoming a DJ or a producer and releasing tracks on labels and just wondering, is that even possible anymore? I mean, you may wonder if it's worth your time learning to use a DAW and learning sound design in light of all these AI tools that have come out. So in this video, I'm going to argue that yes, it is absolutely still worth your time to learn music production in the age of AI. And I'm coming to you not only as a producer, DJ, and someone who teaches music production, but also as someone who studied AI. So I got my PhD in May of 2025 in electrical and computer engineering, and my thesis was on a new learning algorithm that can be used in generative AI to improve performance and resilience of these models. With that said, I'm really concerned about all the hype around AI, and I think it's dangerous both to the field of AI and to people who are being sold promises about the future that in my view are irresponsible to make. So in this video, I'm going to defend the following 4 theses about AI in music production. 1. That AI lacks the ability to be creative the way you can. 2. That you have a permanent advantage over all existing AI systems that is particularly beneficial when it comes to music. 3. That you have the ability to reason in a way that is fundamentally different than any and all AI systems. And lastly, number 4, even if AI could make better music than you, it's still worth your time learning music production. We'll go through each of these in turn, but let's first be clear about what AI actually is, as I think a lot of the unnecessary hype comes from a lack of clarity as to what's going on under the hood, if you will. So let's first see what's going on inside of an AI system. When we talk about AI, which is a very loose term, we're typically talking about the field of what's called machine learning. Now this is a broad term, so we typically break this up. A subset of machine learning is what we call deep learning, which we'll talk more about. And a subset of deep learning are deep generative models, which are models that are designed to generate stuff like images, videos, or text. LLMs, or large language models, are generative models that generate text given some prompt. There are also music generation models like Suno, which are generative models that create an audio file from a given text prompt. Now, all of these refer to algorithms that are run on computer hardware, which means they're subject to proven limitations such as the halting problem and Rice's theorem, which we'll come back to later, though the technical details of these are outside the scope of this video. Let's briefly discuss how deep neural networks work, which form the basis of ChatGPT as well as text-to-music models. In general, you can think of a deep neural network as a system which takes in some input, which we usually represent with the letter X, and produces some output that we represent with the letter Y. You can also think of it as a function, and we'll come back to this later on. For an LLM like ChatGPT, the input is text, and the output is the next word or part of a word that the model deems likely to come next. For generative music models, the input is typically some text, and the output is an audio file. Now, computers can't really work with words or sounds directly, so instead they represent all this stuff with numbers. Text is usually broken up into what are called tokens, where each word or part of a word is represented by a vector. This is a process called tokenization. Audio files can be thought of as a list of numbers, where each number represents the amplitude of a speaker's position at a specific point in time. By representing this stuff with numbers, we can leverage what computers are really good at, which is math. I'm breezing through this, but this is a crucial point we'll be circling back to. Let's go inside the system and see what's going on. So the input to our system is a text description of a song that we want to generate, such as, say, a 90s trance tune. And the output of our system is an audio file. So as we mentioned, the first step is to turn this text description into lists of numbers or vectors through a process called tokenization. Here, each word or part of a word is mapped to a vector. And the hope is that the direction and magnitude of this vector captures some idea of the semantics or the meaning of the word, so that words that mean similar things correspond to similar vectors. This is called an embedding and is typically done with matrix multiplications. So in the example that you see here, the vector that takes you from the word big to the word biggest is similar to the vector that takes you from the word small to smallest. These vectors then pass through these things called artificial neurons, which are very loosely inspired by biology. An artificial neuron is basically a matrix multiplication, where the inputs of the neuron are multiplied by a matrix of numbers stored inside the neuron, which is then followed by some nonlinear activation function that the results of the neuron get passed through. This activation function is again loosely inspired by the way neurons in the brain appear to fire when other neurons connected to it fire. Inside of a neural network, there are many artificial neurons, typically grouped into what are called layers, where the layers between the input and output are called hidden layers. The deep part in deep neural networks refers to networks with a lot of hidden layers. As the text embedding passes through the network, it goes from left to right on this diagram until it reaches the output neurons, which then outputs a vector that corresponds to an audio file or an embedding of an audio file, which is of course what we desire. The values inside each of these artificial neurons are called the network's parameters, and they start out randomly initialized. Then we go through a process called training, where we present the network with corresponding inputs and outputs. With random weights, passing a given description of a song through the network will typically output garbage. However, the point is to train the network to provide the desired output when given the corresponding input. This is done by ever so slightly adjusting the network's parameters so that given a text description of an actual song, the network gets closer and closer to outputting that desired song. You can think of the network's parameters like little knobs that affect what the output is given a certain input. Training refers to the process of algorithmically tweaking these knobs so the difference between the network's output and the desired output gets smaller and smaller. Think of it like tuning an old radio. As you turn the knob or knobs, the sound gets clearer and clearer until you find a certain sweet spot. During training, you provide the network with a massive collection of audio files with known descriptions, so the network learns to output these songs or something close to them. This collection is called the training data and must be collected and labeled by humans. Once you've trained the network, you're ready to perform what is called inference, which is what most users of AI are doing when they interact with it. The knobs are pretty much already set, so all you need to do is take your input, pass it through all the math inside the neural network, and you then have your output, which you can convert from numbers into a more human-friendly format. So in this example, suppose I take a new description, such as an 80s pop song, I perform the tokenization, these will get mapped to vectors, then pass them through all the hidden layers within the network, and then finally get a resulting audio file. Now these algorithms for training neural networks have been around for a long time, since pretty much the 70s and 80s. However, it wasn't until recently that they started actually performing well, and there are two reasons for this. The first is that computers are now fast enough to do the computations required in a reasonable amount of time. You can look up Moore's Law to learn more about this. The second is that we have access to a lot of data thanks to the internet, which was otherwise expensive and time-consuming to gather, clean, and label. When it comes to neural networks, bigger is typically better, both in terms of the size of the network and the amount of data you have to feed through it. If you're wondering why RAM is so expensive at the time I'm recording this video, this is pretty much why. These modern networks have trillions of parameters, and this model needs to be stored in memory and quickly accessed for training and inference. Now I'll make one interesting historical point. ChatGPT was released to the public in November 2022, and there were already talks about AI being conscious before then. One really high-profile case came a few months prior, in June 2022, when an engineer at Google, Blake, claimed that its AI chatbot Lambda was sentient and conscious and had developed feelings. This actually led NeurIPS, what I would consider the top AI conference, to bring in philosopher of mind David Chalmers to discuss issues around AI and consciousness. This conference actually used to be called NIPS, but got renamed while I was in graduate school for what some people would consider to be obvious reasons. Anyways, I actually attended NeurIPS that year and had a few really nice conversations with Chalmers, staying in correspondence with him since. But what's interesting to note is that since then, engineers have become more and more skeptical of the idea that AI is conscious. And this is despite the fact that AI has only gotten better and better. Why is this? Well, recall from our discussion that AI is really just a set of algorithms that are run on computer hardware. And one of the fundamental results in computer science is that computers can only perform tasks that are deemed computable or algorithmic. This means that any computer program can also be executed by pen and paper, with enough ink, paper, time, and I guess dedication. In fact, Alan Turing famously conceptualized the digital computer as operating on moving tape, which forms the basis of all computer hardware we have today. What this means is that any known AI system that currently exists would have the same behavior and give the same result if the computations were done by hand with pen and paper. Granted, with the speed of today's computers, it could take billions of years to do this, but in theory it's possible. So anyone who wants to argue that an AI is conscious or sentient is stuck arguing that doing math with a pen and paper is also conscious, an idea I don't see taken all that seriously. You basically end up having to argue that consciousness emerges, either from the interaction of pen on paper or in some abstract realm that you can influence by writing but can't sense in any other way. It's for this reason the idea that consciousness equals computation isn't taken all that seriously. AI can exhibit behavior that can make it appear to have consciousness, but at bottom it's simply following a step-by-step procedure. Speaking of Alan Turing, this is part of why his notion of the Turing test has been heavily criticized. It asks whether a computer can behave in the way we think an intelligent agent behaves, not whether the AI itself is actually intelligent. Now, if you believe our brains are simply following an algorithm the same way AI has, a view the neuroscience literature calls computer functionalism, this leads to other absurdities, which are outside the scope of this video. The main one I'll briefly mention is that to say your brain is simply following a predefined set of instructions provides what epistemologists, or people who study knowledge, call an undercutting defeater for all of your beliefs. This is because under computer functionalism, your beliefs are formed in accordance with some external algorithm that is not necessarily related to the truth of those beliefs. Since claiming the mind is computation is itself a belief, it ends up being self-defeating. Furthermore, it's clear our brains are not doing anything remotely similar to the process described previously. As cognitive scientists, godfather of AI and Nobel Prize winner Geoffrey Hinton writes, quote, "As a model of how cortex learns, back-propagation remains implausible despite considerable effort to invent ways in which it could be implemented by real neurons. There is no convincing evidence that cortex explicitly propagates error derivatives or stores neural activities for use in a subsequent backwards pass." And it is from here that we arrive at my first thesis, that AI lacks the ability to be creative in the way you, as a human being watching this video, can. An AI system is limited to following a step-by-step procedure. It lacks a will or freedom of the will that you have, meaning it must operate in a predefined sequential manner. This issue of creativity was actually anticipated by the first computer programmer, Ada Lovelace. In 1842, she wrote that the computer, quote, "has no pretensions to originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relations or truths." Computer science professor Selmer Bringsjord created a test for creativity he calls the Lovelace test, named after her. The Lovelace test asks a simple question. Did the AI in question perform a task beyond the explanation of the person who wrote the AI code or someone with comparable expertise? If so, the Lovelace test is passed and the AI is creative. Now, simply surprising results don't count. Bugs or results outside of expectation can be surprising, but they don't necessarily demonstrate creativity. When AlphaGo beat the world champion at Go, it made an unusual and surprising move that wasn't anticipated. This doesn't pass the Lovelace test because it was programmed to play Go and that's what it did. You know what would have passed the Lovelace test? If AlphaGo all of a sudden started explaining the rules of chess, or if it started writing music, whatever that would look like, all tasks outside of its training dataset. At the time I'm recording this video, no one has successfully claimed their AI has passed the Lovelace test. So if AI isn't creative, how is it able to appear so creative and human-like in output? And the answer to this goes back to the details of what's going on under the hood when an AI is trained. It's been shown that deep neural networks are what are called universal function approximators. What this means is they can play connect the dots with any number of dots that you provide. Recall that in order to do anything with AI, we need some way to map our inputs into numbers so we can do math on them. You can think of each input we provide to this network as a point in high-dimensional space. Suppose, for instance, that our inputs to the network are text descriptions of songs that we want to write, and the outputs are audio files. Think of each description song pair as a data point or some dot in this massive space. So, for instance, the description of a 90s trance tune by Ferry Corsten with a JP8000 supersaw lead could map to an audio file corresponding to Out of the Blue, and so on. During training, the neural network learns some function that passes either through or really close to each point. And the key here is that it not only represents all the given points, but it's able to guess what nearby values are. If you're used to the idea of linear regression, where you learn a line of best fit and then use this line to predict new values, the same thing is going on here, just on a massive scale. The function the network learns is able to make predictions between data points and supposedly write a new song. So here, for instance, if we gave it a new description, which is outside the training set, it is mapped somewhere on the function, and the hope is that that place where the function is in between the 2 points also corresponds to a decent song. And here's where we get to a critical point. Creating a new audio file is not hard to do. Even without AI, we can construct an algorithm that can write every single audio file under, say, 4 minutes with a given sample rate and bit depth. This will contain every song ever written and every song that ever will be written under 4 minutes, and of course at that bit rate and sample rate. The difficulty is selecting the audio files that genuinely correspond to enjoyable music. The vast, overwhelming majority of these files will be garbage. They'll sound like noise to us, and a very small number of them will resemble anything like music, and smaller still will be considered good. In other words, the issue is selection, not generation. And where AI helps is it's able to leverage the massive database of existing music that we've deemed good, so it's less likely to suggest garbage. By being able to represent good songs, we hope it's more likely to output a good song when given a prompt than a bad one. With more legit music that covers many possibilities in the training data, we increase the likelihood that the AI will output a song similar to one deemed good. Now, there isn't any magic going on behind the scenes, but I do think it's quite amazing how well this does in practice. For instance, I heard an AI metal cover of the Bee Gees' Stayin' Alive, I'll provide a link in the description, and while I could tell it was AI, I actually thought it sounded pretty good. Tasks like this are actually easy to do using a process similar to what is called style transfer, where you take a new song and, using one technique, project it onto a point in the network's range that satisfies some style or description. Here, the new song would be the original Stayin' Alive, and the style prompt could be music that perhaps has metal in the description. Think of this more as an illustration and one way you could do this rather than necessarily the exact way this was done. The point is, once you have your neural network trained, there's a lot of cool things you can do with it, especially when you have enough training data and a large enough network to handle it. But keep in mind, the reason these models do so well is primarily down to the quality and quantity of training data. In other words, the model can only perform as well as the data goes into it. In fact, if you remove this data, or you train a neural network only on its own output, you end up with what people in my PhD group call mad collapse, often in the context of image models, or simply model collapse. The model ends up forgetting the original data, and the diversity and quality of generated data goes to... In other words, the relevant information is stored in the original human-generated data, and not necessarily in the synthetic data created from the generative model. If the model could really generate something creative, it wouldn't be susceptible to this collapse. In fact, the data it generates can't match the diversity and quality of the data fed into it, let alone improve upon this. So in this example, you can see digits that were created, and each generation that you see here going from left to right is things that are trained on the previous outputs. And eventually you lose the idea of a digit entirely, and these things just become random symbols. They have no meaning at all. So clearly the AI system is not understanding what's actually going on here, and it's kind of degenerating. However, unlike AI, you can exceed the quality and diversity of your previous work. You can generate something new and something unanticipated. And this leads me to my second point, which is you have a permanent advantage over all existing AI systems that is particularly beneficial in music. Now let's take a step back for a moment and ask what music is. Merriam-Webster defines music as, quote, vocal, instrumental, or mechanical sounds having rhythm, melody, or harmony. The key here is sound, and looking up that definition, we have that sound is A, a particular auditory impression, B, the sensation perceived by the sense of hearing, and C, mechanical radiant energy that is transmitted by longitudinal pressure waves in a material medium such as air and is the objective cause of hearing. From here, we may gather that sound involves both air pressure and some form of perception by our ears. You may have heard that kind of annoying question that asks, if a tree falls in a forest, does it make a sound? Some people have used this to argue that some things don't exist unless they're perceived. Let's ignore that question. I think it's clear that if a tree falls in the forest, it will create pressure waves. But if perception is necessary for there to be sound, then this tree doesn't create sound unless there is someone there to perceive it. Anyways, my point isn't to be pedantic about sound requiring perception. Rather, it is to say that our experience of music comes from our ability to perceive it, which may seem like a trivial point. But can computers perceive sound? I don't think so, at least not in the way that we do. And here's why. When we listen to music, acoustic vibrations push against our eardrum, which pushes around fluid in our cochlea. This fluid passes by these little hair cells, which transmit electrical signals through the auditory nerve into our brain that we perceive as the experience of music, or so we think. That last part is pretty crucial and yet not super well understood. There are aspects of our ability to perceive music that is dependent on our brains and how these little hair cells encode air pressure. But there's also more. Stand in front of subwoofers at a big concert and the hairs on your skin will move. Or sticking with the trance theme of this channel, put on System F's Out of the Blue or Ralph Ridge's song Angel and you may get goosebumps or chills. These aspects of music are things a computer cannot understand or cannot hope to understand, even if we grant it is or could be conscious. A computer doesn't have a nervous system and can't respond to dopamine, so how could it know what it's like to have chills? It doesn't have skin or hair cells, so how could it get goosebumps? It's never been to a rave, nor had a childhood where 2000s music creates a nostalgic rush of video games on a beach. Not really sure why that was a thing for a while, but so be it. How can it have warm feelings for a past it's never had? In a point made by philosopher Tom Nagel, AI has no idea what it's like to actually listen to music as a human being. He writes, quote, "If we acknowledge that a physical theory of mind must account for the subjective character of experience, we must admit that no presently available conception gives us a clue how this could be done." The key here is something philosophers called qualia, or the subjective experience of. Even if we grant that a computer could have qualia, which is already a controversial suggestion, I don't see why we should expect a computer to have similar qualia as we do. This is especially the case when it comes to audio, since the way audio is represented is completely and fundamentally different than the electrical signals sent between our ear and our brain when we listen to music. The point being, if you plan on writing music to emotionally resonate with humans, it helps to be a human yourself. It helps to be able to sit in a room, sit in front of a set of speakers, and use these wonderful things we have called ears. All things we can take for granted, but are things a computer cannot do, at least not currently. The advantage you have over AI when it comes to writing music is, quite frankly, an experience of music that computers don't have. Now at this point, a skeptic may object and say, hold up, wait a minute. We don't perceive music directly either. We perceive electrical signals that go into our brain. So what makes the brain so different than a computer? This is a fair point, and to respond to it, let's take a moment to go back to the inside of an AI. What we see is the mathematical manipulation of numbers. We, as the programmer or user, assign meaning to these tokens when we input them into the computer, and meaning to the outputs as well. However, the computer does not necessarily share or understand this meaning. This creates a gap between what is called syntax and what is called semantics. Semantics refer to meaning, and syntax refers to structure or grammar. John Searle famously proposed his Chinese room thought experiment in 1980, attempting to refute the theory that human minds are computer-like information processing systems. His argument illustrates the difference between semantics and syntax, and it goes like this. Searle is alone in a room following simple rules for responding to Chinese characters slipped under the door. Searle doesn't understand Chinese, and yet by following rules in a computer program manipulating characters, he can send appropriate strings of Chinese characters back out under the door. This leads those outside to mistakenly suppose there is a Chinese speaker inside the room. Searle concludes that while computer programs may make it appear to understand language, it may not produce real understanding. Searle claims that this thought experiment shows computers have no understanding of meaning or semantics, they just manipulate symbols. In a similar way, an AI that generates audio files is only manipulating numbers via a predefined step-by-step procedure. These models have no understanding that these numbers represent music and no experience of music. Thus, I think it's fair to say that AI models are not composing music, at least not in the way we think about composition. Returning again to the pen and paper analogy, if I asked you to do the multiplications and divisions necessary to generate a WAV or MP3 song on a piece of paper, you would not all of a sudden hear it. If I printed out the numbers corresponding to a WAV file on a piece of paper, you would not hear the music this WAV file represents by just reading the numbers. You only hear it once the file goes through an analog to digital converter and moves a speaker, creating air pressure vibrations. It also helps that Harry Gordon Rice, about 30 years before Searle, proved that all non-trivial semantic properties of programs are non-computable. In other words, you can't create a computer program that tells you what an arbitrary program does or whether it has a bug. This is why compilers will complain about syntax errors, but you probably won't see any semantic errors. However, programmers can easily answer semantic questions. Why is this? The reason for this is my third thesis. You can reason in a totally different way than any and all AI systems. This has implications for not just music, but basically all mental activity. Philosophers will typically tell you there are three different kinds of reasoning, which are deductive reasoning, inductive reasoning, and abductive reasoning. Let's start with deductive reasoning, which is used to build computers and write programs that are verifiably correct. It is also the type of reasoning used in proofs and mathematics. Deductive reasoning produces valid inferences, meaning the conclusions from deductive arguments logically follow from the premises. Deductive arguments are typically top-down, meaning you start with a general rule or axiom and reason your way to specific examples. For instance, in the classic syllogism modus ponens, we start with the premise, for instance, that all men are mortal as a general rule, and given the specific example that Socrates is a man, can then reason that Socrates must be mortal. Here's an example of deductive reasoning in symbolic form. It can be proven that this forms a valid deductive argument. However, we don't always have access to these general axioms to be able to make a top-down case, and this is where inductive reasoning comes in. Inductive reasoning takes specific examples and reasons to general conclusions, so it's considered bottom-up. Unlike deductive reasoning, this makes inductive reasoning what is called defeasible, meaning it's not airtight. There can be exceptions or unforeseen circumstances. The famous example people will give of induction going wrong has to do with the existence of black swans. Europeans used to think that all swans were white because every swan they had seen for centuries had been white. However, in 1697, a Dutch explorer found black swans in Western Australia, disproving years of common knowledge. Here's an example of induction and action. We can start with observations, such as here are 10 swans. We then observe that all 10 of them are white, and from here we might perhaps mistakenly conclude that all swans are white. And here's an example in symbolic form, and it can be shown that these two types of reasoning are just completely different. You can't get one from the other. Inductive reasoning is the basis of AI, which involves creating a general rule or model from limited examples. And as we discussed, much of the success of AI is due to the massive amount of training data at our fingertips. Induction is typically seen as more accurate the more samples you have, as you get closer and closer to that general axiom you would have in deductive reasoning. Regardless, we use induction all the time. As Scottish philosopher David Hume pointed out, we assume the sun will rise tomorrow because it rose in the past. We can't prove that the sun will rise tomorrow until it actually does, but perhaps the previous occurrences of suns rising provide some sort of evidence for the sun rising tomorrow. Perhaps. As Hume also noted, induction is backwards looking. It involves taking past observation and using them to reason about the future. As a result, it can't anticipate the truly novel or truly improbable, what are often called black swan events or sometimes fat-tailed distributions. Induction is biased towards the highly frequent and highly regular, and against the odd and unexpected. This has implications for music because the kind of music that AI will generate will tend to be within the boundaries of existing genres, and it struggles and will struggle to come up with something new. If you want to create a song in a genre that already exists or is established, AI can or will be able to do that pretty well. But it will have difficulty imagining an entirely new genre or a new instrument. For instance, when Ferry Corsten used the JP8000 Supersaw as a lead in his track Out of the Blue, it was quite literally out of the blue. How could past observations and past music predict that that sound and that synth could be used in that particular way? The inductive basis of AI puts a damper on any creativity it can exhibit. It can mimic and it can do similar, but the paradigm shifting appears out of reach. There's a third type of reasoning we use that appears to be the most challenging for AI. This is abductive reasoning, and is the kind of reasoning used by detectives to figure out the most likely scenario given clues. Like inductive reasoning, it isn't necessarily airtight. Abductive reasoning involves reasoning about alternatives, or what are sometimes called counterfactuals. Here's an example. Premise 1, if it rains, my street will be wet. Premise 2, my street is wet. And then my conclusion is, therefore it likely rained. Now, in the context of deductive reasoning, this technically commits the fallacy of affirming the consequent. This is because there could be other reasons the street is wet besides it simply raining, such as, say, a fire hydrant bursting. However, with more observation, we can see that the neighboring streets are wet too, something we wouldn't expect to see if a fire hydrant burst. With abductive reasoning, we typically evaluate multiple competing hypotheses and choose the one that best fits the data. We use this kind of reasoning all the time when we come to a conclusion about what may have or would be the case if an alternative hypothesis was true, but lacked the general axioms or guarantees we have with deductive reasoning. And AI struggles immensely with abduction. But don't just take my word for it. In a paper titled Assessing the Reasoning Abilities of ChatGPT in the Context of Claim Verification, the authors concluded, quote, our results show that ChatGPT struggles in abductive reasoning, leading them to claim, quote, our study contributes to the growing body of research suggesting that ChatGPT's reasoning processes are unlikely to mirror human-like reasoning and that LLMs need to be more rigorously evaluated to distinguish between hype and actual capabilities, especially in high-stakes real-world tasks such as claim verification. So what does this mean for you as a musician? It means that AI doesn't think or perceive like you, if it even perceives at all. And while it can copy existing music, it can't compose, at least not in the way that you can. With that said, AI can replicate what is already established, especially if there are conventions that can be statistically analyzed. And this is one of the key parts of music in my view. Good music strikes a balance between the novel and the familiar. If you try to be too novel, it becomes shocking or off-putting, so some amount of familiarity is good. However, too much familiarity leads to boredom. The upside of this is the inrush of AI-generated music may push artists to excel where AI struggles, in areas of true creativity. And my hope is this will push artists to be more creative, to come up with entirely new genres or perhaps refusing to work within genres completely. As I always tell my students, genres are there to categorize produced music, not necessarily produce categorized music. Musical conventions are there for a reason, and while you may not want to break all of them at once, you should feel free to bend the rules as needed to get the best result. I want to end by arguing that even if AI could make better music than you, it's still worth your time to learn music production. Now, this is a totally different and independent argument than any of the other points I made, and as a result, I'll be approaching this in a slightly different way. First, a story. I helped teach computer ethics at a research university here in the United States for several semesters. And when grading exams and homework assignments, I would often feed the questions we would give students to ChatGPT and other LLMs to see what it would come up with, in part to just identify if students were copy-pasting the result of ChatGPT. And I'll admit there were times the response that ChatGPT gave sounded really good, sometimes better than most, if not all, the students' responses. And it's got to be discouraging being a student and seeing this AI quickly write out an answer that sounds better than you spending hours, writing a paper and putting your heart and soul into it. But the goal of the assignment isn't really about the objective quality of the responses. The goal is that students practice thinking and writing so they can get better at it. In a similar way, I want you to think about why you want to be a music producer. Is it for fame or status or money? If so, yeah, I think AI makes it a lot harder to justify learning music production. The competition with AI means you'll probably have to put in a lot more work to overcome the wave of slop that's here and will be continuing to grow as time goes on. But what if the goal of learning music production isn't so much about reaching a certain milestone as it is about continually developing your skill? What if it's good for you to practice and learn and make something yourself? Even if your songs are crappy at the beginning of the process, as long as you keep learning and keep getting better, is that truly a failure? I don't think so. Even if AI could generate better songs than you could write now, what makes you think that you couldn't practice and get better at it, so eventually you could make the music that you want and that you can imagine? In the West, we've kind of gotten away from the idea of virtue, as described by people like Thomas Aquinas and Aristotle. To them, ethics is something you practice and get better at, like riding a bike. And just because we've designed cars that go faster than bicycles doesn't mean it isn't worth learning to ride a bike. In a similar way, there's virtue in learning a new skill and getting better and better at it, in that you've done it yourself. So sure, the music you make early on may be something an AI could easily generate or potentially do better. But unlike AI models that are out there, as you are producing, you're also learning the tools of the trade. How to use a DAW, sound design, what sounds good, developing your ear, these sorts of things. With enough practice, you'll get to the point that you can make the music that you want to make. So far, we've been seeing AI and traditional music production as two things in conflict with one another. It's captured well by the sentiment I've kind of modified a bit to be relevant here, which is, I want AI to do my laundry and dishes so I can do things like music production, not for AI to do music production so I have to do the laundry and dishes. However, there are ways AI can be integrated in the music production process in a way that helps artists rather than replacing them. Having an AI run through ideas for a bass line or suggest a lyric in a song when you're stuck could actually be a benefit to producers. It really just depends on how these tools are used. I tend to be a little bit cynical in that I can foresee many simply using these as crutches and just flooding the market with low-quality slop, but if I'm being honest, this was kind of a problem before AI as well. When there's just so much music on places like SoundCloud or Spotify, it's difficult for new and promising artists to gain a footing. The main concern people have is that the rise in AI capability could make it difficult for artists, or anyone for that matter, to make a living. But to be honest, I don't fault Suno or any of the other AI companies for seeing how far AI can go. Someone's bound to do it, and as a research project, it's fascinating. The real problem lies in how the software is used or implemented in the world, structural and social issues that arise at the intersection of technology and its use by humans. I think it's unfair to solely blame the companies that make this technology for that, though they clearly share some of the responsibility. One good place to start would be an agreement to use an AI watermark on things that are AI generated. This would need to come from companies like Suno, and to their credit, I believe they've done exactly this, embedded an inaudible digital watermark so it's clear to at least them that music was generated from their platform. Perhaps that would be even more beneficial when it comes to video creation. Whether or not this watermark should be available to record labels or places like Spotify is a different question entirely, and I'm sure there are other good suggestions out there. I just feel like this video is already getting pretty long. The irony is that many people argue that the accessibility of music production or creation tools sort of democratizes the scene. But personally, I believe it can have the opposite effect, right? It can make it difficult for talented artists to break through, and it kind of concentrates fame and success around a few high-profile individuals who have found a method to sort of rise above all the noise. Unfortunately, at times that method may involve marketing and social media prowess more than creating good music. With too many options available, people often resort to the choice right in front of them, or the easy choice, as psychology tells us. With that said, it's not all doom and gloom. There are plenty of artists like, say, Armin van Buuren, who comes to mind first and foremost, as someone who uses his platform in the scene to help other artists. I mean, I can't imagine how many artists got a chance because they had their music played on his radio show. So, to conclude, I can't guarantee any of the following things. That 1, AI won't transform or potentially even fundamentally transform the way music produced. I can't guarantee that it'll be easy to push above all the slop to get your music signed, that it'll be easier in the coming years. In fact, my guess is it'll get harder, or that it'll be easy to find gigs. Though for this, I do think AI music may make live shows that much more meaningful and compelling to have an actual human interaction with an artist. I actually quit looking for jobs in AI and instead now work for a company that looks to empower artists to host their own festivals, because I find that a lot more meaningful and important than simply making AI better for what often seems to be no reason at all. However, what I can guarantee is that learning music production will allow you to develop valuable skills involved in recording, writing, and mixing, which are, quite frankly, rewarding and most of all fun to learn. And at the end of the day, you'll have something that you made. And that's something no amount of AI-generated music can ever take away from you. Anyways, here are the references, and if you want to see more videos like this, consider subscribing or leaving a comment. I'll also put these in the video description. Thanks for watching, and happy producing. And lastly, I'll just say if you're interested in learning more about both the theoretical properties of AI and how this relates to both their strengths and limitations in the real world, there are 2 books I recommend. The first is The Myth of Artificial Intelligence by Erik Larson. I actually came to a very similar conclusion as Larson did before reading his book, and it actually turns out he and I actually had one of the same professors, which is pretty cool, but he has a really good background, especially in the area of NLP, natural language processing, and has a lot of expertise that's relevant to large language models. The other is The Non-Computable You, which is a book by Robert Marks. So Marks was actually the first president of the IEEE Neural Networks Council, which is now the IEEE Computational Intelligence Society. And in this book, he does a great job going into detail on the more technical and philosophical aspects of AI without losing a non-technical audience, including a great explanation of Rice's theorem and the halting problem, which I didn't get into. Anyway, have a good one, and let me know if you have any questions.